All right, welcome back. We're going to be doing the classwork on central tendency today. But before we get going into the actual classwork, I want to take a moment and go over some things that are confusing for a lot of people from the guided notes, since those are really meant to sort of prepare you for the classwork, for the concepts that we're going into. And then also just a couple of notes on memorization, formulas, and my expectations for this class. So, one of the things that people often have trouble with in the beginning is the symbols that we use in the class and the formulas. So, first of all, I know a lot of people stress out. They make comments about, well, I need to study, I need to memorize these formulas, and really, for me, um, I personally don't find a ton of value in memorizing um, a bunch of stuff. I feel like that's why we have books and that's why we have the internet. And that's why, we have places where we can reference to look up formulas and things like that so that we don't have to have them memorized. What I am really more concerned about is that you understand the concepts. So, for example, a lot of the here's a scary equation that we're going to be seeing very soon for the standard deviation. And see, even right now, I'm having a hard time remembering how exactly this equation goes. It's something like this. And the only way I can remember that is because I know the process for getting the standard deviation, which again, we haven't talked about yet, but just so we have a formula to talk about. Um, and this is very intimidating, right? People think I need to memorize this, but I don't even know what all these different parts mean. The only reason I have this memorized, like I said, is because I know the process of how to get here. I understand the concept of it, and because I've taught this class over and over. When I was working kind of in the real world with statistics, uh, I didn't have this formula memorized. If somebody asked me write the formula for standard deviation, I would have had to look it up because it's just not something that I think is really worth that much space in my brain. When, like I said, you can look it up in a book, you can look it up in your notes, you can look it up on the internet. And this class, in case anybody wasn't sure, all of your tests are considered open book, I guess. I mean, we don't have a book per se, but they're all open note tests. You feel free to refer back to your notes if you need to. That's why you have them. So I am not about memorizing formulas like this. What I really, really care about is, do you understand the concept and do you understand how to interpret? Like if I said the standard deviation for a data set is 3.6, would you be able to interpret that and tell me sort of like, what does that mean? That is way more important to me than you being able to either rattle off the formula or to even do like a problem by hand using the formula. In practice, in real life, when people are doing research, when people are doing statistics, they are not doing all of this by hand. That would be crazy. We have invented so many great computer programs that are designed specifically to take care of that part for us. Why would we waste our time doing long problems by hand where, because we're humans, we're very likely to make little mistakes, and that can throw off things by a big amount. So I trust the computer to know how to do the calculation for me. What's important is that when the computer spits out a number, that I know what that means, that I understand, okay, what does this number mean in the context of whatever it is that we're talking about? Okay, so just to kind of clarify that right up front, because I know people stress out about memorizing the formulas, I will tell you this formula you will see on the final. as you will see this one, which we're going to talk about more in a second, you will see these on the final for this class, but you don't have to come up with them yourselves. All you have to do is if you have a list of, there's like a very short part of the final where you just have to say that this one goes with this and this one goes with this. It's a matching kind of thing. I want you to sort of be able to recognize them and put them together, but you don't have to come up with them yourself. Okay. So hopefully that eases some people's anxiety a bit. I know the formula part makes people super anxious, and I totally get that. Oh, that didn't work how I wanted it. So let's not jump ahead too much. I know that with that scary formula, but today, like I said, we're talking about this concept of central tendency. So to go back to the guided notes for a second, in the guided notes, we have these two formulas. We have this one for the population, and we have this one for the sample. And they look super familiar or super similar, right? So, quick review, which one is bigger, the population or the sample? Population is bigger. So, the population is everybody. And then the sample is like if I choose these different people to actually get my data from, those people are in my sample. They're part of the bigger population, but usually it's really difficult, it's time consuming, it costs money. Not everybody wants to participate in whatever research you're in. It's not really practically feasible for us to get data from an entire population most of the time. A good example of a population kind of sampling method is the census, which we recently had. The census is designed to measure every single person in our country. Because it's every single person, that's the entire population. Then, that really only stays the same for a very short period of time, right? Because people will die, people will be born, people will move in and out of the country. So that population, we get a little snapshot every 10 years of what that population looks like. But then all the rest of the time, it's constantly changing. But we use kind of information that we can gather about different smaller groups to help inform us about the whole big picture, the whole big population. So just remember the population, that's the whole big group. The sample is who we actually collect the data from, right? So these two formulas, they're basically saying the same thing. And let me get rid of this like chocolate chip cookie looking thing over here. Okay. So one thing that you should note is we generally in stats will have two different versions of the formula in a lot of cases, like we do here. We have one for the population and one for the sample. And often those look very much the same like they do here. This is saying add up all your numbers and divide by the number of numbers you just added. This is also saying add up all your numbers and then divide by the number of numbers you just added. These two are actually, you're doing the same thing. What's different is that we tend to use capital letters when we're talking about the population, and we tend to use lowercase letters when we're talking about the sample. Another difference is, and I didn't come up with these rules, I didn't invent statistics, I've just learned it the way that you guys are learning it now. But we use Greek letters to represent the population most of the time. And then we'll use like regular alphanumeric, like the alphabet that we use every day to represent the sample. So for example, for the mean, the population is this Greek letter mu. And This is super dorky, but I'm super dorky, so hope you appreciate this. To help you remember, if this helps you remember, I'm all for it. So this weird symbol, right? It looks kind of like a mix between an M and a U, and so that's literally like how we spell it is mu. And then I like to think of it as because I'm kind of obsessed with cats. I like to imagine it's a little cat and he's saying meow. So that helps you remember what this symbol is when you see this. If the M and the U combined doesn't do it for you, maybe you'll remember it as a cat saying mew. So this is a Greek symbol, right? And so we use that to represent the population. And then to represent the mean of the sample, we use X bar. Anytime you see that line on the top, we just say bar, X bar. And so really all this is for is if I see a problem, if I see, a situation where I see this symbol, then I know it's not only talking about the mean, it's talking about the mean of the population. If I see this symbol, I know it's talking about the mean of a sample. And so just seeing the different symbols informs me that, well, one is referring to that, that it's talking about the mean in general, but also it tells me, is it the population or is it a sample? One that we're going to see very, very soon, if you've been working a little bit ahead, you've probably already seen this. So our next concept that we're going to be talking about is variability and the standard deviation. And we see a similar pattern there where we have a Greek letter, sigma, that's a lowercase sigma, and I'll talk about why that's important in a second. And lowercase sigma, it's like a O with a hat on, or O with a bad hairpiece. And that represents the standard deviation of the population. Whereas if we're talking about the standard deviation of a sample, we use the letter S. Okay, so again, if I see this symbol, I know not only am I talking about a standard deviation, I'm talking about it for a population. If I see this one, then I know we're talking about the standard deviation for a sample. Okay, so that's in practice, really, that's why it's important. A lot of the times it's not, it doesn't seem that important, but it is helpful when you see it to be able to recognize, oh, am I talking about population or am I talking about sample? Okay. And a lot of this information, we're just kind of getting some basics down right now. When we get into actually like doing statistical problems where we're trying to answer questions and we have to use these things in some sort of bigger picture, that's when it's going to start to matter. Right now, it all feels just kind of like, okay, who cares if it's the population or the sample, right? But later on, it is going to start to matter. So that's why we're kind of covering, okay, so remember, if it's a Greek letter, that means it's the population. If it's just a regular letter like X or S, I don't know what to call that. Just a regular alpha letter, then it's referring to a sample. Okay, so just to review that. Now I'm going to go back to, you know what? Let me just leave that up there in case anybody wants to keep looking at that. Okay, so I'm going to switch and focus for now on the sample. And the reason for that is because, like I said, most of the time we don't have data for the whole population. It's too expensive, it takes too much time, it's just not feasible. You can't force people to give you their data. So we're just going to be talking about this equation for a second to review this. So learning statistics is also a little bit like learning a new language. Not only are you learning this new way of thinking, right, which is hard enough, but we also have all these new symbols that we have to figure out what do these things mean. So, and you'll notice I use a simple version. I know in the guided notes, she goes into, and honestly, the fact that I always forget, I think it's the I goes down here and the N or whatever goes up there. I never write it in this more complicated way because I don't need to. In this class, it's always going to be add them all up. Start with the first one and add all the way to the last one. In other classes and other forms of math, or in maybe more complicated stats courses where you're getting more into the formula and theory, these things these things are not arbitrary. They matter. But in our class, they are always going to be the same. So I tend to just forget about them. Why make it more complicated than we need to? This is just saying start with the first one and go to the last one. So I don't really need instructions to tell me do all of them. Okay. So this symbol, this is like I said, we have lowercase sigma, which is the O with the bad haircut. And this is uppercase sigma. That looks like a weird E. All right, so both of these letters are the Greek letter sigma. But just like in English, we have lowercase letters and uppercase letters. So, of course, one more thing to confuse us, right? I think whoever started the whole statistics thing, they must have had some ego issues and they just wanted to feel super smart and make everyone else feel super dumb. And so they made it as confusing as possible. Right? Because why not use a different letter completely? I don't know. But these are both called sigma. So depending on the context, depending on which one, they mean different things, right? So when I say sigma, it depends. Am I talking about a standard deviation of a population? Or am I telling you add a bunch of stuff up? Now, this one, our uppercase sigma, this one really is like it says in the notes, it's the summation symbol. And so it's just a really fancy shorthand for add them all up. Add them up, right? In other classes, it may be like I've taken calculus classes and stuff where you get all sorts of weird gobbledygook with what's at the top and the bottom, and that you may be adding up every third value in your data set until you get to the 60th one or like something weird like that. Then you would, you know, include that other information. In this class, you can always interpret it as add them all up. We're never going to have a case where we're only adding up some of our data values. If you're going to add, you're going to add all of them that we're talking about. Okay, so this symbol, you just want to think of it as shorthand. It means add up whatever the next thing is after it. Okay, as we saw in that standard deviation one, we can say to add up something complicated. In this case, for the mean, we're just adding up something real simple. Okay. So here we're just saying add up. What do we want to add up? Well, we want to add up all the x's. What is x? X is just a value in our data set. So if we have a data set that's 5, 10, 18, 43, and 61, okay? And I tend to, it always helps to put them in order first. That's just a little tip. So this is my first X in my set, X1. This is my second one. This is my third one, fourth one, fifth one, and we could keep going if I had and then whatever. If we had 100 pieces of data in my data set, then the last one would be x sub 100, right? If we had 50, it would be x 50. That little number is just what position it's in. If we were to line them all up from small to big, what position are we talking about specifically? So I could say x5 and we know 1, 2, 3, 4, 5. That's this one. That number at the bottom, and that's what that little I equals whatever, that's what that's referring to. The reason why I don't include this is because we always start with the first one, x sub 1, where I is 1, and we always go up to x sub n, where n is just however many data points we have in our data set. So that's why this whole thing just means add up, starting with the first one and ending with the last one. Right? And that's why I think it's kind of a waste of time to bother including that stuff. So here we've actually kind of identified our two other symbols. So x is just data value, right? We can refer to any of our data values in our data set as x. And if we want to be specific about which one, we could use a little number to say, what position it is in our data set. When you just see like this x, that means just, if I were to just write a plain old x, that would just be some number from our data set. In this context of our mean, we're saying add up all of them. Add up all of our x's. And so we would add up all of these numbers, and that's what goes up on the top of this equation for the mean. As I mentioned down here, n, that's just the number. I like to think of it as the number of numbers. It's really the number, I guess the number of values. It sounds a little less confusing, I hope. It's how many data points do you have in your data set? If we have 100, that n is going to be 100. If we only have 3 data points in our data set, that n is going to be 3. So this equation is saying to get the mean of a sample, or x bar, we want to sum up or add up all of our data values, all of our x's, and you always want to do the top part first, and then divide by the number of numbers we just added up. If you added up 5 numbers, this is going to be a 5. If you added up 50, this is going to be a 50. If you added up 8,000, that's going to be 8,000. Okay? So it's kind of like learning the language of statistics. So I can see this and I can read this equation just as I just said it. I can read this equation as the sample mean is equal to the sum of all the values in our data set divided by the number of values in our data set. And that's all that it's saying. So it's, once you learn what the different symbols stand for, then you can start to kind of read this almost like a sentence, right? It's instructions. It's your instructions of what you're doing. To get the mean of the sample, that is equal to, if you add up all your data points divided by the number of data points. And so I hope that that kind of clarifies a bit from the guided notes, and sort of again on the expectations of of memorization and that kind of stuff for this class. I really, really, really care more about, do you know what the heck the mean is, and what does it tell us about our data? And the mean is our measure of central tendency, which we are going to be talking about further in this classwork. But again, just trying to boil down this complicated looking thing into the basics, okay? So hopefully that helps a little bit. All right, so moving on to our classwork on the measures of central tendency. So what do I mean by central tendency? Well, when we talk about distributions, we're going to be talking about three basic things that we look at first. We've already talked a bit about one, which is what is the shape of the distribution? Is it approximately normal? Is it bimodal? Is it skewed left or skewed right? Is it uniform? Right? And when we look at data, as you'll see pretty soon here when we start, looking at different distributions, it never looks pretty and perfect like this, right? This is just a way of saying the general shape. This may have little pieces that stick out. Maybe it doesn't go all the way up. Maybe it sticks out a little bit. We're just talking about in general, what does the general shape look like? Right? So we've talked about shape a bit. Today we're moving on to our next part, which is going to be where's the center of our data set? And then next classwork, we'll talk about the spread of our data set. So you want to remember these three things are ways that we use to kind of look at our distribution and sort of summarize it, right? What is the shape? Where's the center? And how much spread do we see? So for center, that's where we are today. And we're going to be talking about measures of central tendency as a way of saying, well, whereabouts is the center of this data set that I'm talking about? So um, the guided notes went over three of the very common, three of the super common measures of central tendency that we use. And so those would be the mean, the median, and the mode. Hopefully those words are starting to sound familiar to you. So when should we use each of these measures of central tendency? Well, the mode we usually use for categorical data, right? And so that would be, make this bigger. There we go. So if we're talking about categories, it definitely makes sense to talk about, well, which category has the most? And so you want to remember the mode we're really talking about is the most. It's the highest point. It's um, whichever value in our data set has the most, right? So when we're talking about categories, definitely it makes sense to talk about, well, this category had the most versus the others. To be honest, the rest of the time, we don't really care about the mode very much. And that's just because one single, like if we're talking about a range of whole values, okay, so there happen to be the most at this one particular value, but depending on who's in your sample, that could easily change, right? So that it's kind of arbitrary. So we tend not to talk about the mode when we're talking about numerical data, when we're talking about continuous data, right? Where we're talking about numbers. We really focus on the mode when we're talking about categories of data. In our class, what is the mode with regards to eye color would make sense, something like that. Okay. Now the median is, so let me just kind of clean up a little here. So the mode, remember, is the most. The median is literally the middle value. If we were to line up all of our values in our data set, which one is right in the middle? And by the middle, I mean it has the same number below it and the same number above it. Okay. So the median we usually use when we're talking about ranked or ordinal data. So if we're talking about something where the intervals between the different values are not necessarily the same, going back to one of those earlier guided notes. The median is also used a lot when we have highly skewed data. So I want to point out this highly, because people tend to say, oh, if it's skewed, but no, really, it's only when it's very skewed that we tend to use the median. The rest of the time, the mean tends to be the best measure of central tendency for us, and it gets used a lot in statistics, right? So you've probably heard that medians are better description of central tendency than means for some types of data. When or why are medians better than means? Well, in that case, I would say if we're talking about rank data, or really more commonly when we use it is because we have very skewed data, highly skewed data, meaning that we have some data that really sticks out from the rest, right? We have most of our data's here, and then we've got like a couple out here that really skews things. And that's because the mean gets pulled easily by these values that are far out here, but the median doesn't, because if you only have a couple out here, well, the middle, the halfway point is still going to be somewhere around here. So, even so, we're going to be using means a lot in inferential statistics, and you should wonder why. so, so if the median is better sometimes than the mean, then why do we use the mean so often? You'll see we use the mean for everything in this class. So that's what the rest of this this classwork is really designed to try to answer is what is the mean good for? Why do we use the mean so much? Like what is the value of using the mean over the median when we're trying to talk about where the approximate center of our data is? Okay. So that's the rest of today's lesson. So what do we even mean by middle? Right? You can define the middle or the center in kind of different ways. So let's look at this small distribution, 5, 5, 5, 10, and 20. Now the median of this distribution is 5 because it's the halfway point, right? We have 1, 2 on that side and 1, 2 on this side. So the 5 we can see is literally right in the middle. But the mean of this distribution is 9. So that's pretty different, right? If we're talking about what's the middle of this distribution, if you are going by the median, you would say the middle is 5. If we're going by the mean, we would say the middle is 9, which is not even a number that shows up in our data set in the first place. Right? Both of these things are trying to describe the middle or the center of our data, but they do it in different ways. So I want you to go ahead and pause and in a second and answer number 2. So part A is definitely the more obvious one. How is the median 5 the middle of this distribution? B is the harder question to answer usually. And so I want you to really kind of think about it for a little bit. So how is the mean of 9, if we're looking at this distribution, how is 9 the middle of this distribution? And it helps this, well, maybe it helps, maybe it won't help till after I explain it, but it may help to consider all the differences from the data points to the mean. So think about where 9 fits in here and the difference between 9 and each of these values. So go ahead and take a moment and then and stretch your brain and then come back and I'll explain what I mean. Okay, so let's think about how the mean of 9 can be interpreted as the middle of this data set. And so really what I want you to think about when you're thinking about the mean is to think about balance. Because the mean is designed to find where our whole data set kind of balances in the middle. The median is we just chop it in half, but the mean is all about balance. So to illustrate this, I'm going to show you. So we have 5, 5, and 5. And so when I say think about the differences from the data points to the mean, okay, so if our mean is 9, what is the difference between this 5 and this 9? Well, we have 1, 2, 3, 4 in between, right? It's a difference of 4. 5 is 4 lower than 9. So we get it's 4 lower, negative meaning lower. Well, what's the difference between 5 and 9? It's the same thing. 1, 2, 3, 4. So we also have another 5 is 4 below 9. And then, of course, the same thing again. 5 is 4 below 9. So looking at these first three compared to our mean, we can see that these 3 points collectively are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 on the negative side. So what do we need in order to balance 12 on the negative side? Well, let's compare our 10. Okay, what's the difference between 9 and 10? Well, 1. And 10 is above 9, so in this case, it's a positive 1. Okay, so have we reached balance yet? No. We still have way more negatives than positives. Now let's think about 9 and I never know how far to draw this out. 20. What's the difference between 9 and 20? It's 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 20 is plus 11 because it's 11 higher than that 9. Right? 20 minus 9, 11. So if we look at our negatives that we had negative 12 total. And then we look at the positives that we have positive 12 total. So if we were to add these up, the negatives, the values, the differences below our mean balance out with the differences above our mean. So to show a little different illustration here, right? So we can see that the differences below balance with the differences above. This is what the mean does. It finds what value is going to make it so that the negative differences and the positive differences balance out. And that is exactly what the mean does for us. So any other number that we put in here, if we put 8, if we put 10, if we put, 9.1 even, it's not going to balance out. It's not going to balance both sides of that. So the mean is all about finding what is that one spot where everything balances perfectly, where the differences below balance out the differences above that value. So you kind of want to think of it as like like a teeter-totter kind of thing. What value balances all the ones below with all the ones above? Whatever that number is where we find it perfect balance, that's our mean. That's what the mean does. It finds that balancing point. So hopefully that kind of clarifies a little bit there. So how is the mean the middle of this distribution? Well, it's the middle because it balances all the numbers out, right? It balances the ones below it with the ones above it. And now we're going to talk a bit about measuring heights badly. So this is our first example to kind of illustrate, well, why do we care that it balances, right? What's the big deal if it balances out or not? So this is going to hopefully illustrate, we have two examples, hopefully we'll illustrate a little bit of why that's important a lot of the time. Why do we want to find that balancing point? So here, behind, sorry, it's a little cloudy there. There we go. So this is some data from the National Longitudinal Study of Youth. They collected data from over 8,000 youths. By youths, I mean 15 to 20-year-olds, right? They did this big study where they collected data from 8,000 plus youths. And here we can see a histogram of the heights. So the heights are measured in inches. We can see this is a histogram to review. Look how all the bars are nice and cozy right next to each other. We don't have spaces between them. And on the left side, we can see count or frequency is on our y-axis. Right, wish I could draw on here. With our y being the up and down axis and our x being the side to side axis. Okay, so we can see height in inches from the low all the way to the high on the right hand side. So I want you to take a second and mark on this histogram. If you're thinking, okay, if we want to find the balancing point of all these values that are summarized here, whereabout do you think it would balance? All right, so just make a mark somehow. Honestly, I trying to set up these PDFs is kind of a pain in the butt to explain. When we're in face-to-face class, I give you a workbook that has all of these printed out in it, and you can write all over them. In a digital class, that doesn't really work out. It doesn't really make sense. So I'm doing my best to try to kind of approximate, and uh, so however you can, I want you to eyeball this and think about, okay, where, if I had to consider it balancing, whereabouts would I put my mark to indicate where I think it's going to balance? Am I going to mark down here? Will it balance if I put my little, fulcrum, my seesaw right here? Will it balance if I put it up here? Whereabouts do I think that point is that's going to balance the left and the right? So go ahead and take a moment and think about that. And if you can, somehow mark on your paper or on your device. And now I'm going to tell you that the average is, I don't think it'll let me write in here. So the average actually is 67.05 inches. So 67.05 inches is that balancing point, is the mean of all those values that we see. So take a look back at where you thought it would be. Were you close? And if not, you could update if you want to, adjust if necessary. And just so we can see, 65 or 67.05 inches is about 5.59 feet, just so we know. So, okay, so this is in inches. But what if, and this is a super weird question. This is going to be a weird classwork. So what if instead of measuring everybody to the nearest inch, right? I'm like halfway between 5'4" and 5'5". I like to round up, so we'll say I'm 5'5". So I would be 65 inches. But what if instead of measuring me to the nearest inch, we measured me to the nearest foot and called it a day? Well, 5'5", if you had to round to the nearest foot, I'm closer to 5 feet than I am to 6 feet. And so my new height, if we were to describe my height, is I'm 5 feet tall if we round to the nearest foot. Okay? So take a second and think, what if we only had measures of everybody in this data set to the nearest foot instead of to the nearest inch? Do you think that those measurements are just as good as measuring to the nearest inch? Why or why not? Let's take a moment, think about that, jot down your thoughts. Maybe discuss if necessary in the discussion board. And then to take it a little bit further, if we took so let's say, and let me go back here so we can just see this better. Okay, so here's our distribution. So imagine if instead of all of these, and we know it balances somewhere around 67. So if instead of measuring in inches, this was just in feet, and everybody was rounded to the nearest foot, then how accurate do you think our average would be? How accurate do you think that mean would be? So just to be clear, if we took someone who was 5'3", we would round them down to 5 foot. If we have somebody in our data set, right? So anybody who's below 5'6" or 5'6" or below is going to be rounded down to 5 foot. And everybody who's above 5'6" is going to be rounded up to 6 foot. If we have any super, super tall people over 6'6", then they'll be rounded up to 7 feet. If we have any very short people below 4'6", they'll be rounded down to 4, right? But most of these numbers, I think, are going to round to either 5 foot or 6 foot. So if we changed all those data values to just 5 foot or 6 foot, depending on which was closer, do you think that that average, that the mean of that is going to be very accurate still? Would it be still pretty good? Okay, so think about that. And now I am going to tell you that the mean, and let's see, I think I have more of this in my, right? Well, spoiler alert, okay. Well, so this was this is what we had before, right? The same distribution with the mean of 67.05. Here's what it looks like if we round to just the nearest foot. This is how it works out, okay? So if we took the average of all these 5s and all these 6s, how do you think that's going to compare with this average that we got before? Surprisingly, it works out to about 5.62. If you were to add up all these 5s, looks like about 3,000 5s and about 5,000, maybe a little over 5,000 6s. If we added up all those 5s and 6s and then divided by the 8,000 whatever, we get 5.62. That's the average. If we convert that back into inches, right, because we can convert from feet to inches, then it's 67.44 inches. So that's what we're going to put in here. So we have 67.44 inches. So, and just for comparison, remember before we had the mean was 67.05. When we're rounding, it's 67.44. So this person is, or this average is 5'7" and a little tiny bit. And this average is 5'7" and a little bit, right? Not even 5'7.5". So they work out to be almost the same, right? The first time I saw that kind of blew my mind a little bit. So why do you think that our two means are so close? 67.05 versus 67.44. Even though those measurements seem totally different, right? Rounding somebody from 5'5" down to 5 foot, it feels like we're losing a lot of information there. If we round everybody's height to the nearest foot, that's a lot of inches we're rounding off. So why do you think the means are still so close, even though the measurements rounding to the next foot is really a lot less exact? It's way less precise than measuring to the nearest inch. So you can kind of think about that But really, I want you to really think about this idea of balance, right? Because in both of these cases, we're finding the balance point. So if we think about all of the people who get rounded down to 5 feet and all the people who get rounded up to 6 feet, well, I mean, if we're surely going to have some people who are probably 5'1" and some people who are 5'11". So some people are going to be rounded down, some people are going to be rounded up. 5'2" and 5'10" are both being rounded the same amount, just to different sides. So think about, not everybody's being rounded the same way. So how does that help us maintain that balance, that evening out, that canceling out kind of idea, right? It has to do with these roundings that we're doing, the error, right? If we're losing 2 inches here and we're gaining 2 inches here, that kind of balances out, right? So think about that for a second and then write down your thoughts. All right, so let's look at another situation to look at why this idea of balance actually kind of matters and helps us to hopefully be more accurate about finding the middle of our data set. So here we have this lovely lady. Her name is Penelope, and she's a cow. We also have this dude here, and I don't know what his name is. He's not a cow, he's a man. So let's take a look at this new situation. Now, NPR, for those of you who aren't familiar, NPR stands for National Public Radio. San Bernardino Valley, we've got an NPR station that runs out of our campus. Pretty cool. So recommend you check it out. So NPR, National Public Radio, a while back posted this picture of Penelope, the cow, on the internet. And they asked people to guess, how much do you think Penelope weighs based just on this picture? Right? And this picture was on the internet, is for all sorts of different people. It's for farmers, it's for non-farmers, it's for everybody, right? So I'm going to ask you in a second here, looking at this picture of Penelope, how much do you think she weighs? Right? How much does a cow weigh? And on it's a number 18? No, 8. I'm going to have you write down your guess. And just to give you, a little hint, that guy in the background that you can't totally see, he weighs 165 pounds. So I don't know if that'll help at all in your estimation. This dude is 165 pounds. How much do you think Penelope weighs? And if you have no idea, that is totally okay. The first time I guessed, I was totally off because I don't know nothing about cows. Except that I don't know, they're kind of cute. And they give us milk and beef. Okay, so write down your guess. And then I also want you to think about, how far off do you think your guess is? You think it's too high? You think it's too low? Do you have no idea whatsoever? Just think about it. Okay? And then I want you to think about, okay, if we're trying to measure the weight of a cow, we're trying to measure the weight of this cow, how accurate do you think we can get just by guessing? Right? How accurate do you think we can get just by guessing? And what would you consider accurate? Like if we get within 1 pound, is that accurate? If we get within 50 pounds, within 100 pounds, if we get within 500 pounds, what would you say is, pretty accurate? So in the past, a lot of times people have we've kind of decided, we talked it over in different classes and figured out if it's within about maybe 100 pounds or so. That's probably pretty close. Okay. So they put that picture on the internet. They said, guess how much she weighs? And these were all the guesses that they got. They had over 17,000 guesses collected on the internet. And we can see that those guesses, there's a lot of variation here. There are some guesses that were really low. There's some guesses, like we see a little bump even out here. They're really high. And we see a ton of variation here. So, why do we see all this variation? Why do we see as low as like in the hundreds, low hundreds, all the way up to like 4,000 something? When you think about why do we see all that? And hopefully you kind of figure out, well, it's because a lot of people don't know nothing about cows. And so if you just ask people to guess, especially if they're guessing just based on looking at a picture like this, doesn't seem like a very good way to like if you're going to go buy a cow and the way they weighed the cows to tell you how much they were is they looked at the picture and they go, that cow looks about this many pounds. Doesn't seem like a very good way to measure cow weights, does it? That's what we're doing here. Now, here is the mean guess that they got. So with the 17,000 plus guesses, the mean guess for Penelope was that she weighed 1,287 pounds when they calculated it all out. Now, the crazy part is that's actually really close to the real weight of the cow. She really weighed 1,355 pounds. And all these guesses, from the crazy low guesses to the crazy high guesses, somehow we got within 100 pounds, right? That's less than 100 pounds difference there. So if you look, it's actually pretty close considering that we just looked at the picture. We didn't, but all of these people, these 17,000 people looked at this picture and just totally guessed. Of course, some people are going to know about cow weights, and so their guesses are going to be better than other people's. But I mean, we have some crazy guesses in here. These are probably like people saying, I've had people in past classes say like 200 pounds, and then I try not to get offended that they think I weigh as much as as a cow. But we also see people guessing like 4,000 pounds. So if people are guessing from like 200 pounds to 4,000 pounds, it's kind of crazy that when you figure it all out, it's not that far off. It's within 100. Okay. So why might this be surprising? So whether you personally are surprised or not, why does it seem kind of surprising that we would get so close? Well, I think it's surprising because, like I said, some people have crazy low guesses and some people have crazy high guesses. But then also, why do you think it's so close? Why is the average so close to the actual weight of the cow? So take a moment and see if you can kind of figure that out. So looking at here, how do we kind of get so close? And again, it all comes down to this idea of balance. Right? So if we think about it, there's a whole bunch of different guesses. And there's a lot of wrong guesses that are too low. There's a lot of wrong guesses that are too high. So what happens when there's a lot that are lower and a lot that are higher? They sort of start to cancel each other out, right? The crazy high guesses up here are going to get canceled out by these crazy low guesses down here. And there are more of these low guesses down here, so they kind of eat up more of this high stuff. So if we keep canceling out the low guesses and the high guesses, eventually they sort of find the same middle spot, right? This is kind of neat how that works out. So again, hopefully you're starting to see, why do we use the mean so often? I mean, if we took the halfway point, like if we took the halfway point here, the median of this data set, well, since there's a lot more sixes, the median here would be 6, which is definitely, so that would be what, 72 inches. So that would be a lot further off than the mean in this case. If we found the median here, I don't know what the median is in this case. It's a little skewed. It would probably be a little lower, I would think. Because it's skewed to the right. Oh, I've made such a mess here. Thanks for bearing with me, y'all. Since it's skewed to the right and we know the mean tends to pull towards that skew, then I would guess that the median would be a bit lower. It's probably going to be maybe a little lower. So it would actually be a bit further off from the actual weight if we found the median in this case. So hopefully this is starting to illustrate, like, why is that idea of balance useful for us? Well, it's good because it balances out the errors on both sides. It balances out the bad guesses in this case, or it balances out the bad rounding in this case, so that we actually maintain that middle pretty well, right? So even when we're measuring something in a really bad way, right, and this comes to our next one. So when we measure people to the nearest, like if we measure people's height to the nearest foot, most people would agree that's not a great way to measure height, right? Because you're losing so much information. It's just way less precise. Um, and so if we're measuring people to the nearest foot, that seems like not the greatest way to measure height. It's kind of a bad way of measuring, right? So why would the measurement be bad in that situation? Well, it's bad because it's not very accurate. It's not very precise, right? We lose a lot. For some people, if you're exactly 5 foot or exactly 6 foot, great, that's perfect. But think of all the people who are 5'6" and 5'7". Uh, you know, we're losing a lot of information there. It doesn't seem like the best way to measure. It's a bad way of measuring people's heights. Why we don't do it that way. With the cow situation, again, is it a good way to measure cow weights by looking at a picture and guessing how much the cow weighs? Doesn't seem like a very good way of measuring cow weight, right? So thinking about each of these situations, in both of these situations, the measurements, the individual measurements, were not very good because they're less precise or they're just complete guesses. Right? However, in both of these situations where we start out with bad individual measurements, the average that we get at the end, the mean, is pretty good, right? So in the height in feet example, the mean that we got with the bad measurements versus the mean that we got with the better measurements, why could we consider this still a pretty good average? Well, even when we lost all that information, it's still really close. It's within half an inch, even though we rounded off inches and inches and inches of people's heights, right? So even though we had bad measurements to start with, the average actually works out pretty good because it's super close, right? And then the cow weight, again, looking at a picture of a cow and saying, how much do you think this cow weighs? Not a very good way of measuring cow weight. But when we look at when we look at the mean guess, right? If we look at this mean, how could we consider that a good average? Well, it's pretty good because it's within 100 pounds of the real, like if we really, really measured the cow. So it's close again to the weight of the true weight of the cow, even though these individual guesses are all over the place and can be really bad. Right? So the average in both situations works out to be really close to the true or more precise average, which is good. So then one last question for you to ponder and write your notes down on, and you may want to talk about this in the discussion board with each other. Try to come up with a way of summarizing kind of the lesson about why do we use the mean. So what is the advantage of the mean over the median based on this discussion in this classwork? You'll notice the rest of this semester, we're going to be talking about the mean all the time. We're not going to talk about the median very often, but we're going to talk about, if we want to talk about where's the center of our data, we typically say the mean. Why is that the case? Why do we usually use the mean? Why is the mean typically a better way of measuring the center than the median based on our discussion? And again, you're going to want to go back to this idea. Okay? So hopefully that gets you thinking and kind of illustrates why the mean is so cool. I'll see you guys soon.